I have shown you how to classify systems using a graph and algebraically using ratios. I will now show you how to classify systems using determinants. If a non-zero delta x or delta y is divided by a zero, which is delta c, the system is inconsistent. In other words, if you had x equal to delta x over delta c, and this amounted to a number non-zero, but delta c is 0, then that's an inconsistent system. Now, if you have a 0 delta x or delta y divided by a delta c equal to 0, the system is dependent. That's the second classification. That is, if you had x equal to delta x over delta c, and that was amounted to 0 over 0 like that, then it's immediately classified as a dependent system. But as long as delta c is non-zero, then a unique solution will be the result, and that's classified as a consistent and independent solution. If delta c is non-zero, then there is a unique solution and the system is consistent and independent. Three by three systems of equations will now be solved by using determinants. I will first have to show you how to calculate a 3 by 3 determinant. There will be two methods explained, and you should learn one of them well. The general method explained in the first one can be extended to larger sized determinants and is considered the more basic of the two. The other method will only apply to a 3 by 3 determinant and none of the others. The 3 by 3 determinant is reduced to the calculation of 3 2 by 2 determinants. In other words, there's a reduction in size of the determinant we begin with, but the trade-off is that you have several 2 by 2 determinants to work with. And this is the method. Let's use the following determinant then. 2, 3, 5 in this column, 2, 1, minus 3 in this column, and 1, minus 2 and minus 7 in this column. This is a square arrangement of 9 numbers, as you can see. You will have to memorize several steps. Each number along the top row serves as a multiplier of 2 by 2 determinants, constructed in a very special way. Observe, and I'll repeat what I said. The top row of numbers 2, 2, and 1 serve as multipliers And this is how it's constructed. We'll take the upper left-hand corner number, which is 2, and it must be multiplied by a determinant that's 2 by 2 in size that results when we take out the top row and the left column. You see what is left. It is this pair, this square arrangement of numbers in this corner. Arrangement, square array. 1, minus 2, minus 3, and minus 7. The next number, which is 2, take that off. 2 again. We take out the row and column that it's a member of. That 2 is part of that row, and that 2 is part of that column. And if you take those rows and columns out, what is left is 3, 5, and minus 2, minus 7. But one other thing you're going to have to remember is that you have to put a negative sign in front of that 2. So the 2 is going to be multiplied by the determinant 3, negative 2, 5, negative 7. And finally, the last number in the upper right-hand corner, which is 1, if the row and column is removed from the determinant that contains that number 1, you end up with this arrangement of numbers in a square, and that makes up your third determinant. So it's plus 1 times 3, 1, 5, negative 3. Well, each of these 2 by 2 arrangements of determinants, and we write 2 multiplied by negative 7 subtract positive 6, followed by negative 2 multiplied by negative 21 subtract negative 10. Subtract negative 10 can be replaced by positive 10. And finally, plus 1 multiplied by negative 9 subtract 5. Continuing, we have 2 multiplied by minus 13, minus 2 multiplied by minus 11, plus 1 times minus 14. Continuing, minus 26 plus 22 and minus 14. This amounts to negative 40 plus 22 is negative 18. The second method of evaluating determinants was suggested by Cyrus, a mathematician of the 18th century, and so it has very limited application. Taking the same determinant that I used earlier, we had 2, 3, 5 this way, and 2, 1, minus 3 this way, and, sorry, it was 2, 1, negative 2, negative 7. What he did was this. If you repeat the first 2 columns outside this vertical line, 2, 3, 5, 2, 1, negative 3, and perform multiplication in the following way. Here is a diagonal of numbers, 5, 1, 1. If you multiply those across that diagonal, the answer is 5. Multiply the next 3 numbers along the diagonal, and the answer is plus 6 times 2 is 12. And finally, the third diagonal of 3 numbers along here is negative 21 times 2, which is negative 42. And now take the sum. The sum is 5 and 12 is 17, negative 5, negative 25. You repeat the process along a diagonal this way of 3 numbers. You end up with the product minus 14. For that, the next diagonal of 3 numbers are multiplied along here, and the answer is minus 20. 2 times minus 2 is minus 4 times 5 is minus 20. And finally, the last diagonal of 3 numbers are multiplied, and the answer is minus 9. Take the sum of these 3 numbers, and the answer is negative, that'll be 3. Backwards subtraction here is negative 18. And that's the value of that 3 by 3 determinant. Now, the solution of the 3 by 3 system of equations continues in much the same way as it did for the 2 by 2 system. In other words, you will calculate delta C, the 3 by 3 determinant of coefficients of the variables, Now, this is a determinant which is 3 by 3, and it equals a number. We know how to calculate that number now. Delta x is the determinant with the x column from delta c replaced by the constants. Delta y, constructed in the same way. I'll just shorten that to determinant, det, with constants in the y column of delta c. Similarly for delta z. So there we have delta c, delta x, delta y, and delta z. All these determinants are numbers. X is going to be the number which you get when you divide delta x by delta c. Y will be the number that you get when you take delta y and divide it by delta c. And finally, z is the number that you get when you divide delta z by delta c again. 2x plus 2y plus z equals 3. I will write the coefficients in black and write the variables in later. So I have 2x plus 2y plus z equal to 3. And that is my equation 1. 2x plus 2y plus z equals 3. 3x plus y minus 2z is equal to 5, and that's my equation 2. 3x plus y minus 2z equals 5. 5x minus 3y minus 7z is equal to 5, and that's my equation 3. 5x minus 3y minus 7z. Look at the arrangement of 9 coefficients on the left-hand side of the equal sign. And you can see that I've arranged the terms in their proper order. We ignore the letters x, y, and z completely. And we write then that delta c is equal to 2, 3, 5, 2, 1, minus 3, 1, minus 2, minus 7. There is delta c, the coefficients of the variables, the 9 of them. This is equal to 2 times 1 minus 2 minus 3 minus 7, followed by minus 2 times 3 minus 2, 5 minus 7, followed by plus 1 times 3, 1, 5 minus 3. Continuing, this is 2 multiplied by negative 7, negative positive 6. Then we have negative 2 multiplied by negative 21, positive 10, which is negative 11, plus 1 multiplied by minus 9, minus 5, which is minus 14. This amounts to negative 26, positive 22, negative 14, for a total of, so delta C is negative 18. Now, what is delta X equal to? Delta X is equal to the arrangement of 9 numbers that you get when you take the constants and put them in the X column of delta C. So we put 3, 5, 5 there, 2, 1 minus 3 there, 1 minus 2 minus 7 there. This amounts to 3 multiplied by minus 7 minus 6. This amounts to minus 2 multiplied by minus 35 plus 10. And finally, we have 1 multiplied by 5 times minus 3 is minus 15 minus 5. This is equal to 3 times minus 13 minus 2 times minus 25 and plus 1 times minus 20. That amounts to minus 39 plus 50 minus 20, and the total there is minus 9. For delta Y, we start again with delta C and take out the center column and replace it with 3, 5, 5. So we have then that the 2, 3, 5 there, the 3, 5, 5 there, and the 1 minus 2 minus 7 there. Starting with 2 and multiplying it by the 2 by 2 determinant down in this corner, we end up with 2 multiplied by minus 35 minus minus 10, or plus 10. We have negative 3 multiplied by the determinant 3 times minus 7 is minus 21. Negative negative 10 is plus 10. And 1 times this corner determinant, and we have plus 1 times 15 minus 25. Simplifying, we have 2 times minus 25 minus 3 times minus 11 plus 1 times minus 10. This is equal to minus 50 plus 33 minus 10 for a total of minus 60 plus 33. And finally, delta Z is the determinant you get when you start with delta C again, take out the Z column of numbers, and put the constants in their place. So we have 2, 3, 5, 2, 1 minus 3, and 3, 5, 5. So this amounts to, once again, 2 multiplied by 5 plus 15 minus 2 times 15 minus 25, and plus 3 times minus 9 minus 5. This is 2 multiplied by 20 minus 2 multiplied by minus 10, and plus 3 times minus 14. This amounts to 40 plus 20 minus 42. And that value is equal to plus 18. I meant to write this in red. There we have calculated delta C, delta X, delta Y, and delta Z. Now to continue with this solution, I'm going to remove my equation. X is equal to delta X over delta C, and that is equal to, look for these values, minus 9 over minus 18. And that is equal to 1/2. We have Y is equal to delta Y over delta C, and that is equal to, where do we have it, minus 27 over minus 18, and that is equal to 3/2, positive 3/2. And finally, we have that Z is equal to delta Z over delta C, which is equal to, there's delta Z, 18 divided by minus 18, and that's equal to minus 1. And there you have the solution to the system x, y, z by using the method of determinants. So therefore, x, comma, y, comma, z is equal to 1/2, 3/2, and minus 1. You will notice that there is one slight advantage in using the solution by the determinant method. And it is that only one of the variables can be solved for without involving any of the others. There's no backward substitution required as in the method of elimination. The next type of system I want to deal with is referred to as nonlinear systems. In some nonlinear systems of equations, the nonlinear variable may be temporarily replaced by another variable which is linear. And the solution continues, assuming that the system is linear. The procedure is a transformation of a nonlinear system to a linear one. And the linear system is solved for in the usual way, either by elimination or by determinants. Only a 2-by-2 system will be considered. After you have solved the linear system, use the answers back where the nonlinear variables were replaced by the linear variables. In a 2-by system only, by which I mean we are only going to deal with that size, in a 2-by-2 system only, use the linear solutions and place them in the statement where the linear variables were written in place of the nonlinear ones. Having done that, then you would solve for the nonlinear variables. For example, 6 over x minus 5 over y equals 7. This is equation 1. And 2 over x plus 1 over y is equal to 5. Equation. As you can see, we have the variables in the divisor here. Consequently, these are not linear variables. Let's look at the nonlinear variables a little differently. I'll just put 6 minus 5 equals 7 for now. 2 plus 1 equals 5, and write the variables in different colors. In other words, 6 over x is the same as 6 times 1 over x. Similarly, 2 times 1 over x. Minus 5 times 1 over y, and plus 1 times 1 over y. There you have your nonlinear variables isolated within brackets. And as I explained earlier, what you must do is substitute these nonlinear variables with linear ones, and it's simply this arrangement. Let the letter p equal 1 over x and the letter q equal 1 over y. Now, using p and q instead of 1 over x and 1 over y, I have the following. 6 minus 5 equals 7 with p here and q there. Similarly, 2 plus 1, I'll ignore the 1, and write 2p plus 1q equals 5. There you have a linear model, or a linear system, placing the nonlinear one. And since we know how to solve linear systems, of course, we can find out what p and q equal. And let's do that. If I multiply number 2 by 5 using the method of elimination, 5 multiplied by 2, I will get 10p plus 5q equals 25 for equation 3, and 6p minus 5q equals 7 is equation 1. And this equals, then, when we add and eliminate q, 16p equals 32. Therefore, p is equal to 2. If we substitute p equal to 2, let's say in equation 2 along here, it seems to be the simplest one to use. If p is 2, this is 4. Subtract 4 here, q is equal to 1. I have now solved the linear system. P is 2, q is 1. But how does that solve the nonlinear one? Well, you go back to the original statement where you made the transformation from one system to the other, where you let the nonlinear variable be a linear one, and that was in this statement here. Where we let p equal to 1 over x and q equal to 1 over y, that's where the transformation occurred. So if p is equal to 2, what we're saying is that 2 is equal to 1 over x. Solving for x, 2x equals 1. Therefore, x is 1/2. Similarly over here, where q was equal to 1 in the linear system, go back to the statement where the variables that was nonlinear was replaced with the linear one, and in place of q, write the number 1. We conclude then that 1 is equal to 1 over y. Well, this one's easy, obviously, therefore y is equal to 1. So the solution is then for x comma y, the nonlinear, from the nonlinear system, that x comma y is equal to 1/2 comma 1.